Hello, it is Advent of Code, day 3 for 2021. If my voice sounds a bit rough, it's because my lung condition's been bad recently. Last night anyway. So, creaking noises. Two binary numbers called the gamma rate and the epsilon rate. The power consumption can then be found by multiplying the gamma rate by the epsilon rate, okay? This I inputted some string of binary numbers with a width of 5. My input has a width of 12. Okay. Cool. Guessing that it's probably 12 for everyone. I'll use a U32 just to give me space, but I'll clamp it so that we only work on the last 5 bits. That way it's got space in case other input files have wider binary widths, though I think that's unlikely. Most common bit in the corresponding position. Okay, so if we sum the bits of a column, if we count the number of times that a column has a bit and it's greater than, and that times 2 is greater than what you do all of the numbers. I guess, do we have an odd number of inputs? What do we do if there's a tie? Let me scaffold this. Scaffold day 3. And then I can just have a look at my input and see how long it is. My input for day 3 will appear here in a second. Okay. Gamma rate is this binary number. The epsilon rate is calculated in a similar way. Use the most common bit, the least common. Okay, so that's just going to be not. So we only need to calculate one of them because these are a binary not operation from each other. Okay, that should be nice and easy. How many of these do we have? We have exactly 1,000. So there could be a tie, but I'm guessing it's just coded not to have a tie. Otherwise, that would depend on there might be some edge case behavior. Okay, cool. Parsing this input's actually going to be really annoying. So we need a width, which is going to be a U32 for consistency with everything else. And we need a data, which is going to be a vec of U32. Okay, so that's what we need to get to. It's kind of a pain. We're going to just have to write a more naive parser, I think, for this. So we'll say, we'll still use norm, but character complete. Line ending we'll still need. We will need character. Multi-separated list. We'll need map, obviously. We'll also need map res to do our binary parsing. So binary number is equal to I'm just going to say width is 1 second, I've had a knock at the door. I will pause my recording. That was my weekly shop getting here. Now where were we? So input, I was just gonna get the width like naively for now. What's my create error? I've got like a... Just using strings apparently. No data. Lines is an iterator, right? Oh, next, not first. Okay. And then our binary number parser is going to be a map res of guess we'll take satisfy. Map res of satisfy C. And we're going to map that into num, and then we're going to say it's like from str radix. Yeah. Okay, so that's the binary number parser written. Okay. Oh, many one satisfy. Okay. Okay, and then we need to. I'm just going to remove that and see how that behaves. Could not convert. It's because this uses past result, which is a bit different. I mean, the parser would fail because we're using. The parser will fail because we're using many one and line one, so there must at least be one of one width. So we know our parser would fail. So just taking a default value of 0, that 0 will never be exposed if the data is back. Okay. And then we will say, you still. Oh, now you're a vet car instead of a str. You know what? Just take numeric. That's like a thing, right? I know we have alpha. Presumably, we have numeric non-character complete. Rust. Nom instead of num. Rust. Non-character complete. I don't really want to use. Do we have bin digit? No, we have oct digit 1. How's oct digit 1 implemented? Implemented as oct digit. Okay. Satisfy recognizes one character. That satisfies a predict. Is take while? Is take while is a binary operation? We can probably do that though, but. Honestly, I think this will fail because the parser will fail. So if I just say digit 1, we use digit 1 instead. Because the parser will fail if it's not a binary number at the from str radix step. From str radix. Doesn't it like about that? Cannot infer. Consider giving binary number a type. Okay, we'll do it like this then. We'll pass I in there and then we'll call I on that. It'll actually. It's because it doesn't. It'll like it in a second. I think once we have the rest of the code in. Numbers is separated list of line ending and binary number. And so then we have got a final result of new pass is equal to map numbers into data pass input width data pass input. Does not. Width? Oh, it's because width is a U size. Width should be a U32. We'll just cast it there. Okay, that should, in theory, work. Let's have a look at the result of passing that. And we will derive debug on this. We can inspect it. Let's just bring in their nice, easy test case. In our tests, test input is equal to this. Okay, and then that is test assert task. I'm gonna bring my own framework here. Parse1, task1, test input, and I have gonna be equal to just got parse obviously, so I'm not using a multi-parser setup, which my framework does support actually. We might see that at some point. Parse input doesn't implement debug. Oh, because I didn't put a capital D here. How to do that? Okay, now hopefully test should give us some meaningful output. Yep, and that looks like the numbers we have. 4, yep. 30, yep. 22, yep. 23, 21. Okay, I'm happy to say that that's correct. Okay, cool. So now we have our input. We're going to need a function called, I'm going to call it bit clamp. And it's going to have, we're always going to need to use the same bit clamper. So we'll make a struct bit clamper that has a width, and I'm just going to put the width in here. And then we're going to implement bit clamper to have a clamp function, derive copy clone. That takes in another U32, and this thing's job is to say that it is the num and 2 to the power of self.0 minus 1, and that should in theory produce correct bit clamping. So now in here we can say let c equal bit clamper input.width, and now for num in input.data c.clamp num. This should give us the same numbers as before because these are all of the appropriate width. Well, you can't take ownership, that's fine. It's copy safe, just copy it. Then run the test. Same outputs, so I'm happy. Okay, cool. Okay, so now we know that that works. We have our bit clamper. Let's actually think about the next thing we need to do. So we're going to need that at the end, just to make sure that our numbers, you know, when we do not, we need to make sure that we only care about the tail of the operation. So now we need to actually count these bits. So the best way to do this. We need to count how many ones there are on the final bit. On the next one, so 0, 1, 2, 3, 4. Okay, so for bit in 0 to input width, so that's going to give us our right shift amount, and then we only care about last bit is a bit clamper 1. So this here is a input bit. I'll call this input clamp, and then this is called a last bit clamp. So in here we need to do last bit clamp dot clamp input. Okay, we need to say for number in input dot numbers iter input dot data iter. Last bit clamp dot clamp number right shifted by bit, And so that should give us a 1 or a 0. So we can say that that equals 1. We can make this a filter. And we can count that, and then that is going to give us a count for every single one of them. So now in here, if I say print line this, we should see, and then, oh, hold on, we care if that count times by 2 is greater than or equal to our input width. That's the actual thing we care about. Let's make this actually stay usize. Let's not corrupt it here. And then in here, let's make this a U32 here. Okay, what is this output? It wants us to... Sure, that's fine. References. True, 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 true. Okay, well that's clearly not the case. What is this count? Five, 7, 8, 5, 7. Is that correct? 1, 2, 3, 4, 5, 6, 7. Hold on, so first one, 1, 2, 3, 4, 5 is correct. 1, 2, 7 is correct. Oh, you know what it is? We don't just need width. We also, we don't want to compare this to that. We want to compare this to data.length. That is actually the reason that failed. So now I'm expecting we see let's get rid of our debug statement so we can actually see the bits that are going on in here. False, true, true, false, true. False, true, true, false, true. Okay, so this gives us now the correct booleans for the bit parsing. Now all we need to do is we need to use those in a thing. So we're going to do 0 input.width.fold, starting with a value 0. Out item. Okay, and then we need to do this calculation here. And then if it's true, so if this, let me just say, and this is called the epsilon number. So if all of that nonsense is true, then we return out and 1 right shifted by 1, left shifted by 1. You are called bits, you should be called bit here. Width, it's a fold, and bit. Oh wait, no, hold on, I'm being silly. To input widths, like that. There we go. Okay, now why do you not like this? Oh, because we don't have an else. So else, out, you know what we can do? We can just do it like that. You don't like the parentheses there, sure. Why are you expecting it to be a unit type? I want this data to fall through so I can left shift it. Okay, I mean, I can just left shift it anyway, but Old should not need me to... Okay, well it likes it like that then. That's kind of annoying. It's probably to do with the way the parentheses here work. Okay, so that gives us our epsilon number, which now if we... so let's just do our final output here. So this is going to be a U32, and our number is going to be epsilon times by not epsilon, but then that is input clamp.clamp, not epsilon. And that should, for this, give an output of... Hold on, this is going the wrong way. This is going to give us, this is going to be the over left shifted. We actually need to go backward here. This should be dot rev, I think. Okay, and this is going to give us an output of, what did they say? 198 is what they got for this value. So let's try 198 in our test harness. We'll run that test. Failed. Left 0. Right is 198. Why is left 0? Left should not be 0. This is definitely true sometimes. We can verify that by debugging it. And seeing, hopefully, that it is true sometimes. True, false, true, true, false. Yep, as expected. So then this should be... Oh, it's not out and 1, it's out or 1. That's the problem. Okay, that's that fixed. Run the test. 836. That is a bigger number than we wanted. Okay, what do we get for epsilon? Let's just check. Let's check our epsilon gets computed correctly. So we're expecting an epsilon of 22. We have an epsilon of 44. Interesting. That means that we are... Oh, it's because we're just left shifting it one too many times. Epsilon needs to be right shifted once more at the end. Okay, so that... Basically, because we're writing and then left shifting, it gets pushed one too far over. So we need to just bring it back by 1. Perfect. Okay, so now that one passes, we can run this on our real data. So let us run this and see what we get. This big number. Submit. That's correct. Okay, part 2. Next, you should verify the life support rating, which can be determined by multiplying the oxygen generator rating by the CO2 scrubber rating. What? Okay, a value can be found in your diagnostic report. Finding them is a tricky part. Both values are located using a similar process that involves filtering out values until only one remains before searching either rating value. Start with the full list of binary numbers from your diagnostic and consider just the first bit of those numbers. Then, keep only the numbers selected by the bit criteria, the type of the rating value. What? Okay. For which you're searching, discard numbers which do not match the bit criteria. If you have only one number left, stop. This is the rating value. Okay, hold on. So determine the most common value, 0 or 1, in the current bit position, and keep only numbers with that bit in their position. 0 and 1 are equally common. Keep values with 1. Okay. Using the same diagnostic, start with all 12 numbers and consider only the first bit of each number. There are more 1 bits than 0 bits, so keep only the 7 numbers with a 1 bit. Okay, that's easy to do. We keep those. Then consider the second bit of the remaining 7 numbers. 0 bits. Okay, so we're looking for the number that gets closest to our desired number. Okay, so our epsilon value was like 10110, and then the closest value to that is 1011 and then 1, because it's only a single bit off. So it's the first value that is a minimum number of bits off is what we're after. Okay, that's fine. That's actually easy to find. We do want to forward the data from here though, so we're actually going to return. We're going to build a custom output pub struct task1 out, and this is going to carry the epsilon and the output, and then we're gonna. Do I use display? I can never remember what I actually use to do my checks. It's debug. And then in here, I print debug. Okay, so let's do implement debug task1 out. And we just want to do f dot write f self dot epsilon. Okay, that should be fine. Okay, so now we can forward our task1 out by saying task1 out epsilon output. We actually only want to print the output, not the epsilon, so output. And this shouldn't change the result of our big one here. Nope. Okay, but now what I can do is I can come in here and I can forward task1 into task2 and get my task1 out in here, like so. That's part of the whole harness I've built for doing advents of code. So now we have our epsilon here, so we need to find the number closest to our epsilon and closest to our, let's just forward both. We have epsilon, we have, they called the other one gamma, I think. We'll say let gamma is equal to input clamp dot clamp not epsilon. Epsilon gamma and epsilon, and then we don't even need to output that in here because we can do that in our formatter. Epsilon times self dot gamma. Okay, so now when we run this, we should still see the same thing ending in 944, except I removed this from here, so still ends in 944, but now we have access to our epsilon and our gamma value. Okay, so now we need to search through for the first value that has a minimum difference. So let's say, we're going to do, again, bit masking here. And in fact, I think I want to remove my bit clamper and just, or make this a more explicit operation. Yeah, actually, I think that's the best way to do this, is rather than storing this, because I only use it in one place, I only use it here. And then again, this bit here, I only use here. So let's bring those in. And masking is pretty obvious in operation, so I'm not too worried about that. Okay, so what we're going to do is we're going to say, although it is this whole 2 to the blank thing still, right? Yeah, we care about the inverse of our bit clamp, actually. So what we want to have is we want to have a so to inverse clamp it is to say we actually care about removing the last n bits. So this is num and this nonsense, but instead of keeping the last 10 bits, we want to remove the last few bits. Okay. You know what? I think I've come around to the idea of just making these floating functions. So num, and we'll call this clamp u32. And we'll call this clamp u32. Just a bit of on-the-fly refactoring here. Don't worry about it. Now in here we need to say clamp this by input.width as u32. We can remove the bit clamper. And then in here we say clamp this down to 1 bit. And that should clamp this down to 1 bit, and that should have, I think that does have better clarity. Okay, cool. So now thinking through what we need to say 4 bits similar from input.width down to 0. So from 0 to input.width. Why would I put from in? So that's going to give us our bits similar, but we want the reverse of that. I'm going to leave the OK at the bottom for now, just so it compiles. Okay, so this is going to start at our input width and say, hey, is there, and we're going to seek, is there anything wholly similar? Now, the way we're going to do that is we're going to say for data in input.data. And we want to say, is data, is clamp inv data of bits. Okay, we actually want to go bits dissimilar. Is that how you spell dissimilar? Or bits bits wrong? Let's call it bits wrong. This doesn't get reversed. Okay. So clamp inv 0 should, in theory, be a no-op. Inv clamp, okay. And then we're going to clamp that to data to input width. So that is going to give us all of our numbers, but with the tail zeroed out for this. So this is our let data override. And then our let target is equal to, and we want to find it for so the oxygen generator for the CO2 scrubber, I assume we're using the epsilon. 0 bits. Yes. Okay, so we're going to say we're trying to find both the delta and the epsilon. We'll start by doing this in 2 passes. I'm going to combine them into 1 pass after. So we'll say let epsilon here is going to be equal to task1 out.epsilon, and we're going to do the exact same operation of inverse clamping it to the bits wrong and then clamping it to the input width to get rid of those leading ones we introduce. And then we'll say if data is equal to epsilon, or we'll say data wrong and epsilon wrong. And then here what we will do is we will say let mute let mute oxygen equals none. Say if let some oxygen, or if oxygen is none, we'll just say if data is and oxygen is none, then we say data wrong. We say oxygen is some data, and we do the same thing here. We say gamma wrong doesn't like bits wrong. Bits wrong is because bits wrong is a U size, right? Yeah, U32. Oh, that's U32. Okay. Input.width is also a U size. This is where maybe I should. I'm going to do that. It's needed as a U32 way more often than it's needed as literally constantly. I think now that I fixed a bug. Be a U32, thanks. Does the word as appear anywhere now? Go away. Okay, I'm content with that. Hopefully the compiler is too. If not, we'll track it down. So gamma wrong is the same process, but using task1 out gamma. And we'll do the exact same thing, but we will say if gamma wrong is epsilon wrong, we'll call this check so that we can break out of it here at the end. We'll say let mute CO2 is equal to none. Change that to CO2. We'll change this to data wrong is equal to gamma wrong. And we'll set CO2 equal to some data. And then we will say if oxygen is some and CO2 is some, then break out of check. Okay. And so now down here, what we're looking for is let oxygen equal oxygen dot okay or no oxygen rating found, which shouldn't happen, but you know, just in case. CO2 equals CO2 okay or no CO2 rating found, which again shouldn't happen. And then we need to, what do we need? We need to multiply them together. Multiply them together. Okay, so we'll do oxygen times by CO2 for our final output here. And so that is our U32. And what are we hoping for here? 230. Okay, let's see if that is correct for task 2. Don't expect it to be. I expect something to be wrong. Oh, right. Task 1, task 2. How does this work now? Oh, hold on. Have I built an assert task with flow? I have built an assert task with flow. I need to mirror it here. There we go. Okay, left is 230, right is 230. What? What? They're the same. Left is not equal to right, but they are both 230. Now I am very confused. Task 2 format equals format. Task 1. I mean, the test might fail, but it's correct. So let's just see what output it gets, and then I'll figure out what's wrong with the test in my own time. Not the right answer. What? Okay, so maybe the test doesn't pass? What is this value here? It's 230, right? I've not gone insane. And they said it should be 230. 220. 220. I'm what? What? Okay, I can't read. That's the reason the test was failing. Okay, let's see what number it finds for each of them. Print line binary formatted oxygen and print line binary formatted CO2. What number do you find for each of these? You find, for this one, you find 10110, which I think, oh, hold on. As there is only one number left, the oxygen generator rating is 10111. 10110. Data is the input data. I'm considering from right to left. No, I'm considering from left to right. I'm checking first do they all match, then do 4 of them match. Oh, but yeah. And then do 3 of them match. That is correct. Keep the number with a 1 in that. In the 5th position, there is an equal number of 0 bits and 1 bits, so find the oxygen. Is this just that I'm doing greater than or equals here and I should be doing greater than? And it doesn't affect task 1, but it does affect task 2. Because that kind of off by 1 could well be the cause. Okay. Now our first value here is correct. No, wait, it's not. 10111. Does 10110 appear in this list? It does. And that is our epsilon rating. That's our gamma rate. Okay, I have gamma and epsilon the wrong way around. That's what's causing this problem. Ah, crap. Gamma underscore, and rename this one to epsilon, and then rename this one to gamma. And then in here, this is actually the gamma underscore, and this one here is actually the epsilon. This one here is actually the gamma. Is that the problem? That I have epsilon and gamma the wrong way around? Yes, I had epsilon and gamma the wrong way around. Okay, that's fine. Oh wait, hold on. That wasn't my test. That was just me trying to run it. Still wrong. Oh, you know why? I probably am not. You not gamma and you are epsilon. Task 1 out. And then in here, I'm now reading the wrong ones in. Right. So you should now be epsilon and you should now be gamma. Now, hopefully, the test passes. No, it does not. It's actually just flipped. Right, of course it's just flipped. Which makes it even more wrong. Wait, hold on. I've confused myself. Let me make sure that the epsilon and the gamma are the right way around. So epsilon is. I'm also been on my lunch break for 41 minutes. I might have to go back to work in a sec. Gamma rate and the epsilon rate. The gamma rate is the binary number which is what I had before. But the gamma is the correct. Can we debug? Can we just print out let's see what gamma and epsilon are, please. Gamma we are reporting as 22. Epsilon we are reporting as 9. Okay, so now gamma and epsilon are the correct way around. So that was an issue before. Now, our epsilon wrong here is measuring our epsilon wrong here, and then our data wrong. Our oxygen is based on what? Oxygen generator rating, the most common value 0 or 1 at the current bit position. Least common value 0. So oxygen is based on our most common, which is gamma. Okay, that's still not going to have fixed it because I've just flipped things around again. But at least now we're a bit closer. So the issue is I am being clever, trying to be too clever with my scan here. Like, let me emphasize that. This does not. I need to just rubber duck it, which is really annoying. So let's say we start with our first pass through where we're saying that there are no bits wrong. This is going to fail on all of them because let's actually check that data wrong is what we think it is each time. So this should just be losing precision basically over time. Small test so that it doesn't fill up half the screen. Okay, so we start with our bits wrong, our data wrong, being that there is no data wrong at all. In which case we have 4, 30, yep, okay. Then we say that we do not care about. Okay, I found the source of the problem here. This should not be 7. This should just be zeroing the last bit. So why is it not? Bits wrong here would be 1. Inverse clamp. It's our inverse clamp operation that doesn't make any sense. I can determine that basically. So let's quickly figure out what's wrong with our inverse clamp operation. So let x equal 0, 0, 1, 0, 0. Let clamp inv clamp equal, and let's say we were going to clamp this to, we want to lose the last bit of precision. So to lose the last bit of precision, so this is, if this is a 1 or a 0 to lose it, we need to AND this with 0, be 1, 1, 1, 1, 0. All ones and a 0. Now that value there is equal to, I thought, not this. If we say 2 to the power of 1, that gives us 2. Minus 1, that gives us 1, and not 1 should give us a 1, all ones and a 0 there. Let me only look at the first number. First number goes 4, 4, 4, 0, 0. Okay, that is actually correct. 4, then still 4, then still 4, and then it suddenly is 0. Okay, and then the next one, say I do skip 1 in here. This will tell us the second one's values. Still 30, dropping that one. Then we fall to 28, yep. Then we fall to 24, yep. Then we fall to 16. So that is how the precision is being correctly reduced, by just like not caring about the last values. So I'm actually happy with this algorithm. The question is just, why is this getting back 1, 0, 1, 1, 0? Because that is correct. There are an equal number of 0 and 1 bits, so to find the oxygen generator, keep the one with a 1. Okay, so it is being caused by deliberate dodginess in whether or not we are using greater than or equals here. But we had it as greater than or equals before, so this shouldn't magically fix it. No. Yeah, because that wouldn't change our rating. So maybe we can't use part 1, because the value we're actually searching for is different. In the 5th position, there are equal number of 0, 1 bits, 1 each. Oh, you need to run the reduction on only what's left. God, that is awful. Okay, we can do this, So we say function find gamma, and we put from some input set of u32 and a width. And our find gamma function is going to be basically just what's in here. Except we are going to just return it, and then this is not input width, this is just width, and then this is just input, not input data. $n. Okay, so now we have let gamma is find gamma input dot data reference to input dot width. Okay, that is really silly. It means that I can't use this kind of smart scan approach that I've built, which I was hoping would work, because we need to ignore values once we discount them. What we are functionally actually going to say here is we're going to have to say, we'll have to do this twice. So we'll have to say, let's say we're going to find our oxygen first. Okay, so this actually is almost like a recursive approach. Yeah, this is a recursive approach, so task to recurse, or find CO2 rating. Let's start with find CO2 rating, or find oxygen rating. Find oxygen rating. Man, okay. So then in here, our input is going to be a bunch of these and a gamma is going to be this, and a width is going to be needed. Okay, so we have all of these, and we're going to find a oxygen rating. So if input.len is equal to 1, then we return input. That is just the base case. I don't think it says... okay, yeah. And we return input 0. Okay, so there's our base case. Okay. Now, if that is not the case, then what we need to do is say let gamma is find gamma on our input and our width. So that's going to give us our gamma rating for what we know of that's left. And we also need a bits a precision that increases. Bit care, I guess, is the actual thing we care about here. Oh boy. And then so our task 2 solution is actually going to be, just to start with, we'll say this is an option U32 because it could fail. Oh no, you know what, we'll say let oxygen equal find oxygen rating of our input.data, our find gamma, which we don't need to pass the gamma in because we're going to find the gamma each time. We no longer need to care about task 1. Okay. We are no longer a forwarding operation here. Our width is going to be our input.width, and our bit to care about is going to be input.width to start with. We care about the leftmost bit. And then this is okay or cannot find oxygen. Okay, and then we will have a similar one implemented called CO2, and this will be oxygen times by CO2. CO2 rating, I'll find oxygen rating. Okay. Okay, we are also going to write a function called find epsilon. Find epsilon from gamma. Gamma is going to be U32, alpha is going to be U32, and we're just going to move this nonsense in it and say find epsilon from gamma, and we will pass in gamma. Okay. Now find CO2 rating, and we will just copy this down here for now, say find CO2 rating. And for now it's just going to return none because we haven't implemented it yet. Okay, now this one here, we find the gamma rating of what remains, and then we only care about a specific bit. Now to get a specific bit, what we do is we say let input, so we're going to do input let next inputs is equal to input dot iter dot cloned dot map input. We'll call this data. Okay, so now we need to look at the nth bit of our data and see if it is equal to our gamma, the nth bit of our gamma. So we say gamma right shift by bit care minus, and this should start by caring about the minus 1, so the fourth bit, 0, 1, 2, 3, 4. Yeah. Bit care and 1 is equal to This is filter and then collect into a vector is equal to data bitchar and 1. Okay, so there's our next inputs, and then we say find oxygen rating of next inputs, same width, and bitchar is now 1 lower. So that should find the oxygen rating. Let me just comment out the existence of CO2 for now. And all I want to see is that this finds the oxygen rating of 23. It doesn't like things. What does it not like? It does not like find epsilon from gamma also needs to have a width. We will then need to pass in here as input.width. Please just tell me that we are the number 23 in decimal. Attempt to subtract with overflow. Where do we subtract anything? Oh, bitchar. Right, okay. Yeah, sure. So bitchar can't go negative. At the start here, what we'll do is we'll actually say we operate on bitchar -1. We'll do that. And then we can pass in input.width. Input.width -1, which would have messed this up anyway. Okay. Please be 23. It's 23. Okay, perfect. So now all we need to do is repeat the same algorithm, but for the gamma. Find CO2 rating. Parsing into find CO2 rating, and instead of finding the gamma, we find the gamma and we say let epsilon find epsilon from gamma and width, and then in here we use the epsilon. Oxygen times CO2, this should now pass. Okay, finding the CO2 rating is wrong. Am I using the gamma anywhere still? No. Okay, why is this wrong? Epsilon by bitchar, data by bitchar, next inputs width bitchar. Input first copied. Okay, let's have a look in here. Then consider the bit 5 remaining numbers. In the third position, there are an equal number of 0 and 1 bits. Is this where the whole greater than versus greater than equals matters? That could just be the case. Why do we get 220 again? Is this not a symmetrical operation anymore? Oh no, it's not. Oh, I hate that. That's awful. Okay. Find gamma. We're no longer going to be able to do our naughty bit hack to find gamma. We now need to find it manually from an input. Now we care about if it is less than or equal to. Okay, that is an annoying change, but means that our find CO2 rating here can just find epsilon from input. And now this should give us back 230. Yeah. Okay, I really hate that, but if, you know, that's the way they want the question to be, then that's the way they want the question to be. And so this is our answer. And with 4 seconds before my lunch break ends, that is that finished.